Does aromatic start?
Cyclic structure.
Has to be cyclic. Next.
Completely conjugated ring.
Completely conjugated with ring. The ring needs to make every atom in the ring should be completely conjugated, which basically means what? sp2 is the common one. Obviously it can be sp as well because you need unhybridized p orbitals. So you should be able to have resonance throughout the ring. Okay, what's the third criteria? It has to be planar, which is kind of related to 2, because if the planarity doesn't exist, the p orbitals are not in the same plane, you can't have resonance, right? Please remember, the requirement for resonance is that the p orbitals must be parallel to each other. If the p orbitals are not parallel to each other, then you can't have resonance. So that's kind of why we need planarity. Okay, what's the fourth?
Pi e's equals 4n plus 2.
So the pi electrons, this is called the Huckel's rule. For the number of pi electrons must equal 4n plus 2, where n is any number from 0 onwards that you can plug in as long as the math gives you that answer. Then it is aromatic. That is called Huckel's rule. I'm probably pronouncing it wrong, but that's what it is. Everybody, does that sound okay?
Yep.
How do we decide if something is anti-aromatic?
All the same, except
All the same as 1, 2, 3 are the same. And then, so same. And then what's number 4?
Pi electrons equals 4n.
Must equal 4n. Right? Again, n can be anything from 0 onwards. And then if 1 is not satisfied, or 2 is not satisfied, or 3 is not satisfied, those are called anti-aromatic. If one, we don't even have to think about 4.
none?
If one of these 3 are not met, whichever 3, if 1 is not met, or 2 is not met, or 3 is not met, if any of these is not being satisfied as a condition, then it's non-aromatic. Any not met. Does that make sense, everybody?
Mm-hmm.
Okay, and then we started looking. We just saw 3 examples, just FYI kind of thing. But let's look at a few more. So let's start with the smallest ring. How many carbons would there be in the smallest ring?
3.
Right, so cyclopropene, right? You can only have one double bond in a 3-membered ring. Would you call this aromatic, anti-aromatic, non-aromatic? Just going to draw a few more. So here we have cyclobutadiene, then we have cyclopentadiene, then we have cyclohexatriene. Are you guys, is that right?
No.
No, what is it?
Benzene.
Not the same thing. And then we have, how about cycloheptatriene? How about cycloocta? How many double bonds can we fit in? 8 carbons, right? Okay, how about, well, let's do these first, then I'll draw more. Okay, let's start with cyclopropene. Aromatic, anti, non. Why non? It's not completely conjugated. Why do you say it's not completely conjugated?
sp3 hybridized carbon.
That carbon right there does not have any unhybridized p orbitals, so it cannot participate in resonance. Everybody okay?
Yep.
Okay, how about cyclobutadiene?
4n.
So is it, go through the list, is it cyclic?
Yep.
Is
It's
it completely conjugated?
Yes.
yep. sp2.
Is it planar?
Yes.
Yep.
And then if 1 yes, 2 yes, 3 yes, then we go to 4. How many pi electrons does it have?
4.
4.
So which formula does that fit? Does it fit 4n plus 2 or 4n?
4n.
4n.
So if it fits 4n, what is this then?
For,
It's anti-aromatic, exactly. Anti-aromatic is less stable. This is the baseline, as we were saying. This is the standard. This is what we expect. Anti is less stable than expected. Aromatic is even more stable than the baseline. Okay, how about cyclopentadiene?
Non.
Non
Non.
again. Do you all agree? Because there's that.
SP free
How about
hybridized carbon.
this guy?
Aromatic.
And why? And we've already seen that benzene is aromatic, but now hopefully you understand why it is aromatic, because 1, 2, 3, and 4. The total number of pi electrons is 6, and 6 pi electrons is equal to 4n plus 2, where n is equal to 1. Isn't that right?
Yep.
Okay. How about cycloheptatriene? It's, are you sure?
It's non.
It's non.
Sorry, I was thinking about the Ochem.
Okay, good. We'll get to that point in a second. Absolutely, this is non because right there. Okay, now this guy is actually a little bit trickier than you would think. Now, the way I draw it on the board, it looks like it's planar. Isn't that right? It seems like it's all in one plane. So if it is all in one plane, condition 1, yes. Condition 2, yes. Condition 3, yes. Assuming it's in one plane, what would this be? Aromatic, anti, or
Anti.
do you all agree?
Yes.
Is everybody okay with that?
Mm-hmm.
But guys, can you guys pick up some model boxes, please, very quickly? Go, 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 go. Come on.
Where you can flip it like that.
And make this for me, please.
One for both? Or?
Yeah, one for both of us.
Yeah, one box, whatever. Let's make this. And actually, you might need 2 boxes. No, you should have enough double bonds. Here you go. Good. Let's make this.
So we need double bonds.
No, yeah. Ooh, we don't have, here.
It has 4 double bonds.
We have one.
That's for. We only
You
need
have
4.
2 minutes to make this, so let's not spend too much
4
time.
double bonds? How,
You
what
know
else?
how to do this. Get
Give me
8
some.
carbons, go. Not these ones though, those are sp2 hybridized carbons. You need 4 double bonds.
I think the gray ones are SP2 hybridized.
Okay, give me some.
Yes, exactly.
Give me 2.
Yes, snap it in. There we go. Good, good, good. Yeah, black's not needed, the gray ones.
The gray ones are SP2. Yeah, they're SP2. Come on. Oh. These pieces are so crazy.
Got it?
Yeah.
We're
Perfect,
we're
good.
starting to form ours, but it's hard. I'm trying to form mine. Thank you, Mark. I think we can each use the same model.
Yeah.
Oh, what?
Here.
Do you know how to make an octatron?
So what
Because
else?
I'm probably gonna make benzene if I do this wrong.
Okay.
We want an octatron. Octatetraene. Got that one.
So wait.
So we made 3 double bonds.
How come
So
they
now we
have-
need 4 double bonds.
Good. May I borrow? So the black, it's okay for now, but FYI, the black pieces are
I think we have to do,
Ugh, come on.
I think we need to do it gray.
Yeah, we need to do gray.
gray one.
We definitely need to do gray.
Okay, so there, and then what?
Okay. But now it's are we done?
Oh.
Everybody? 4 double bonds, connect them. That's it.
Can you tighten that one for me, please?
Yes.
Oh, yeah, it's gonna be on.
I thought I already had it. Oh, forget it.
Yeah, forget it. Maybe we can use. Maybe we can share the model.
No, Well, we have to.
Yeah, we have to.
Let's make another one.
Okay.
What, Mark?
So here's the
No, I mean
question
another one of
have. Everybody, can we do this, please?
No, it's not. On mine is it has an electron.
We're trying to assemble ours.
Okay.
But it's not conjugated, right? So still would be.
Cool. I see that you guys there. Whoa, I like that. What did you try to do, Emma? You tried to make it planar, right? Does it like it? If you force it to be in one plane, do you see how the bonds are distorting it a tiny bit? So do you think it wants to be planar?
It can't be.
No, it doesn't want to be planar.
There
And
we-
if you just give it a little tiny shake, what happens? There we go. Becomes non-planar. May I borrow that for a second, Vincent? If it's non-planar, would the p orbitals here be parallel to the p orbitals there? Would the p orbitals be aligned in a parallel manner?
I think it's wrong.
No.
This is wrong.
If they're not aligned in the parallel manner, is it completely conjugated? No.
No.
Does that make sense, everybody?
Yep.
So what is this really? Fine, if you make it planar, it looks like it's anti. But in reality, what is it? Non. It's non. It is non-aromatic because it doesn't want to be planar. Too much stress there in the ring for it to be forced to be planar.
What am I doing?
Do you, say that again?
Is that okay for benzene though?
Is it? Make it. Please make it. That's the only way you'll know if it is or not, if you make it.
Oh,
But let's do it quickly.
Forced.
That's cyclohexane, not benzene.
Oh.
Totally different.
SP2.
Those are sp3 hybridized carbons. These are sp2 hybridized carbons.
So it
Guys,
doesn't
are you
go
all
planar, right?
convinced?
Yeah, it doesn't work.
Everybody okay that this is non? In reality, it's non because in reality, it doesn't want to be planar.
Yep.
Everybody okay?
Yep.
Okay, now I want you to take the model you have and then quickly, and you might need to combine pieces because maybe this is not, we don't have enough in each box, but I would like for you to make this from, oops, wrong. Make this for me. It's cyclodecapentaene.
What?
But, what? You know what? But it
Cyclopenta.
needs to look like this. Please notice, is this E or Z?
E.
Is that E or Z?
Z.
Is that E or Z?
E.
This one? Z. How about this?
Z.
And how about this?
E.
Meaning two bonds, two double bonds are E and the remaining three are Z. So please make exactly this for me. Let's do this fast.
If planar, but that was not planar.
Yeah, I mean, that's what we said. If it were planar, you would say
So we
that,
need
but in
to add-
reality,
Oh,
it
okay.
is not
So we need
planar.
to add 4 more.
It's reality. It
That's a
doesn't-
non-aromatic,
Yes.
non.
1, 2, 3, 4. We need to add like 4 more carbons. No, we made a cyclooctane, so we need 2 more carbons. And we have 5 doubles. We have 5 double bonds.
So, the way
Okay,
it's
this
drawn
is-
on paper, I mean on the board, paper, whatever, what would you expect it to
Don't use
be?
that.
Would you expect it to be aromatic, anti-aromatic, non-aromatic because it looks planar? What do you think? Sorry? Aromatic? Why? So prediction is because
Aromatic.
the total number of electrons is 10 pi electrons, which fits what? 4n plus 2?
Yep.
Right? Because what is the value of n?
N is 2.
Agreed? Let's see what it really is. So please go ahead, make the model, then we look at it. But you have to make. Oh, you're putting, I'm like, that's not 10 carbons. Okay, you're putting the rest together.
So we can take off.
So 3 of the 5 bonds are cis, the other 2 are trans. It looks like that. Good. Can it be planar? Yes. Pause. Go ahead.
I'm trying to make mine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many pi bonds do you have? 1, 2, 3, 4, 5. Okay.
For hydrocarbon, I would agree because one of the carbons.
Maybe we need to destroy this and just mark. I have 10 carbons and 5 pi bonds.
So you have enough?
Yeah.
Do you need anything?
Um,
Do you need single ones?
no.
Look very carefully.
Okay, let's see. There is no middle. There's no middle.
Yeah, there's no middle carbon.
Okay, so we have 3. Where's the 3?
We have 5 pi bonds.
Yeah, so
Already counted.
1, 2, and 3. No, this is
1,
only
2,
2.
3, 4, 5. It has 5 pi bonds.
So the ring doesn't have the string. You can do it, but when you do it, you want it.
Would be like that, right?
I guess, sort of. And let's see if it can be planar.
No, I can't.
You're forcing it to be planar.
You guys see that? Can it be planar? Sure?
What?
Think again.
No.
Can it be planar?
No.
Something's not looking right here, may I?
Yeah.
Yeah. I was trying to make the model.
No, I mean, so you got to follow the drawing there.
Yeah, well, we.
And I was also trying to
Well,
follow.
this is cis. These two have to be trans.
Oh,
Oh, they have to be trans.
Those two bonds have to be trans and 3 of them are
Yeah,
cis.
we missed that.
Follow the drawing, please.
I was trying to follow.
Okay,
I
so
was
does
trying
it
to
want to
follow
be
the drawing.
planar?
Okay, so do trans.
Okay, so this one, so these two are trans.
On the side of the tree, there's 3 here.
Thing to happen.
So how is it trans?
So, you guys answer the question.
How do we do trans?
Trans,
This one.
here we go. So there's a single here. Let me see. I guess this is how we do trans. That's a trans.
Are these trans?
And is that could be trans.
I mean, you got it right? But then which one?
Oh, what the heck. I totally busted up my model.
What? Why do we want to bond them? So what? Does it want to be planar? What's going on, guys? The structure is on the board.
I'm trying to
No,
follow.
you got to. Okay,
I'm trying
I
to-
know you're trying, but you got to do it. I get that part. Let's shift it. I mean, if that connects, let's switch it so that I want this. Hold on, this on that. But I want this to be.
We want it to be trans.
Yes. So I'm gonna switch it. Then, yeah, I mean, we've used models before. We know how to use them. I don't know.
We've used models.
Why? You gotta push right.
See, that's the only thing you change is these to make it.
Because I just want to connect this to that.
Oh,
part, right?
so I just flip that other one around?
So I want, this is that. I want this one. I want Z here. Right, this one should be Z. Oh, I see, I know what I'm doing. So I want this E, so I'm going to connect it here. And then I want this to be E as well, so I'm going to switch that.
Yeah, we swap that. Alright,
It's the same thing. I mean,
there we go.
okay, guys, let's come back, please. Can we do this faster? Everybody,
What does that mean?
is it really aromatic?
No,
Why is it not aromatic?
because the hydrogen bond.
What do you mean hydrogen bonds?
The hydrogens, getting each other's way.
So therefore,
It's not planar.
which hydrogens are we talking about? This hydrogen right here and this hydrogen right here, right?
Yes.
Do you see how they are hitting each other?
Yes.
Do they? Is that a good thing?
No.
So to avoid that steric interaction, what does the ring need to do?
Flip out.
It needs to twist out of planarity. It's not planar. If it's not planar, what is the designation you would give it?
Non-aromatic.
So even though it has the right number of pi electrons, it has resonance and all of that, It's not aromatic. It doesn't have that added stability that aromaticity brings in because of those two hydrogens. Make sense, everybody? Yeah? Cool? Questions?
Wait, so what other compound is there that is aromatic? That's not
What about cyclonamine?
I'm not good at drawing, so be
Okay.
patient with me.
We're all passing with an A. And I'm passing away.
Beyond 8 after 8, guys, can we please do this?
Yep.
After 8 carbons, you can assume planarity. 8 is still 8, it may or may not be planar. After that, the rings get big enough that you can, like for example, this guy, it can be planar, except that causes those hydrogens to bump into each other. So after that, like if you see a drawing like this, it's totally okay to assume planar because it's big enough to be planar. We okay?
So if
So-
we saw that one, it's okay to assume planar? because it's not
Exactly.
an eight?
Assume beyond this, assume to be planar.
Okay.
Absolutely. So, is it cyclic?
Yeah.
Yes, it's
Is
cyclic.
it completely conjugated?
Yes.
Is it planar? You can say yes beyond when rings get this big.
Okay.
Everybody okay?
Mhm.
Now, what is the total number of pi electrons? 1, 2, 3, 4, 5, 6, 7, 14.
8, 10, 12, 14. Yep.
Agreed? Now, which formula does it fit? Does it fit 4n or 4n plus 2? Does it fit 4n plus 2?
Yes.
What value of n would that be?
Free.
So what would you call this? Aromatic, anti-aromatic, non-aromatic?
Aromatic.
Absolutely. So the question to you, or the answer to your question, Dash, is absolutely. There are many things.
Okay.
Although, will we ever work with something like that? The answer is no. For us, benzene is, at least as a neutral compound, benzene is aromatic. Everybody okay? Yes?
So if instead of the two hydrogens in the middle of that, we put a carbon-carbon bond, that would not be completely conjugated?
Are you talking about, to make sure I'm understanding what you're
So if I replace the
seeing?
two hydrogens and
Yeah.
then with a carbon-carbon
Close
bond.
it.
So you're basically taking, is that what you're referring
Yep,
to?
yep.
Absolutely, and that's a category of compounds we'll get to in a little bit.
But that's
Those are
not
called,
aromatic.
no, it is aromatic.
Oh, it is?
Because here's one benzene, here's another benzene fused together. So why don't we do that right now? So this is hydrocarbons, neutral hydrocarbons with conjugated double bonds with different size rings. But then another category of aromatic compounds is fused benzene rings. So if you have fused benzene rings that are basically fused together, those benzene, can't spell benzene, those will all be aromatic because each ring is aromatic. Each benzene ring is aromatic, so the fused system is also aromatic. So the one that Eric is referring to, have you guys heard of naphthalene? That's naphthalene. It is definitely aromatic. So here is one benzene ring, here's another benzene ring. You can also draw it as totally fine because obviously those are two benzene rings that are fused together. Absolutely, naphthalene is aromatic. Phenanthrene, anthracene. I mean, there are all compounds that have benzenes fused together. Those are all aromatic. Yeah?
Is the circle a symbol for benzene or is that aromatic?
You tell me.
Well,
What does the circle mean? Anybody?
Resonance.
Exactly, that's all it means. It's basically saying that those double bonds are resonance delocalized.
Just do a giant circle.
You can, but it just gets, you can, I guess if I were to do that, instead of putting a giant circle here, which makes it a little unclear, I might put something like that.
A plus sign?
That's what the circle means, is that the pi electrons here are delocalized across the whole ring. So, absolutely. So, coming to the question, there's a huge family of compounds. What they have are benzene rings that are fused together in different shapes. That's naphthalene, aromatic, phenanthline, aromatic, anthracene, aromatic, and there are lots of others. So yes, if there is a structure where seemingly benzene rings are stuck together, overall that system is aromatic because each benzene ring is aromatic. Does that sound okay, everybody?
Mm-hmm.
Okay, cool. Now let's go to a different category of aromatic substances for us. Oh, before I go there, actually. Another category of aromatic substances are ions. Can ions be aromatic? The answer is absolutely. Same rules, same criteria, same rules. So, for example, please tell me, if we have cyclopropene, is it aromatic, anti, non? Non. Everybody agrees?
Yep, non-aromatic.
Now let's say I do some reaction where the hydrogen, one of the hydrogens on the sp3 carbon is taken by a base as a proton. What will that create? Anybody? If cyclopropene were to lose a proton, what will it create? Plus, are you sure?
Negative charge.
Please look at the curved arrows, right? A
Negative
carb
charge.
anion,
Yep, a carbon anion.
agreed?
Yep.
We already said this is non-aromatic. Okay, fine. What about this ion? Is it aromatic, non-aromatic, anti-aromatic? So we still have to go through the same list of criteria. Is it cyclic?
Yep.
Is it completely conjugated?
No. Or yes. Free elect.
I'm going to pause here. Kinda. I like that answer. Kinda. Because there are two considerations that we should go through. According to Vespa, what is the shape of that carbon atom?
Trigonal planar.
According to Vespa, what is the shape of that carbon with a negative charge? Let's go back to Gen Chem.
Okay.
Vespa. First thing is you got to think of electron groups. How many electron groups?
4
is that
electron
carbon?
groups.
So if there are 4 electron groups, what's the predicted shape?
Tetrahedral.
If it's
Tetrahedral.
tetrahedral, what's the hybridization then?
SP free.
Guys, why pause? If anything is tetrahedral, what hybridization state do you expect it to be? Do you all agree? So that is one consideration. If this is sp3, which is what Vespa predicts, it should be tetrahedral. If this is sp3, should that carbon participate in resonance?
Yes. No.
No.
Do sp3 hybridized carbons have unhybridized p orbitals?
No.
So if an atom does not have unhybridized p orbitals, can they do resonance?
No.
So if this is sp3, can this atom do resonance?
No.
So if this is sp3, is the ring conjugated?
No.
Do you all agree?
Yes.
Is everybody okay? So what does it become? Aromatic, anti, non? Is everyone on the same page with me? Okay? Cool. Here's my second assumption. That's based on Vespa. But is Vespa always right? The answer is no. Here's my second assumption. Let's assume that this carbon is actually sp2. You guys with me?
Mm-hmm.
If this don't do that, let's process it, because you'll be surprised. if this carbon is sp2, which orbital do those electrons live in?
The p orbital.
You guys okay?
Mm-hmm.
If they live in the p orbital, can they do resonance?
Yep.
So then, in that situation, cyclic, completely conjugated, planar. What is the total number of pi electrons?
4.
2 and 2. The electrons in resonance, total number of electrons that are delocalized by that. Do you all agree?
Mm-hmm.
4. Which formula does that fit? Does that fit 4n plus 2 or 4n?
4n.
Everybody agrees? So if that were sp2, what would you call this ion? Aromatic, anti, non? So next question I have for you is, what's better? Energetically, in terms of stability, in terms of energy, is it better for something to be non-aromatic or anti-aromatic?
Non.
According to stability, if we have stability, where is non?
Between anti and
It's the baseline. That's our baseline, that's our expectation. Where is aromatic in this chart? Is it above non or below non in stability?
above non.
And where is anti?
Below non.
Of course, energy and stability are inversely related to each other, but the point is, if the choice were being between anti or non, what's a better option?
Non.
Do you all agree? Yes? So that's what I would go with then. There's no benefit for this carbon atom to be sp2 hybridized. Energy is not, stability is not being gained by this carbon being sp2 hybridized. Everybody okay with me? Sure? Get it? But what if the same molecule, cyclopropene, somehow were to lose a hydride ion? What would it become? If it were to lose an H minus, what would this become? Louder? It's getting rid of H minus. What would it become? Do you all agree?
Mm-hmm.
Right? Why were you hesitating? Agreed?
Mm-hmm.
So, now let's do the same thing with the carbocation or this whole system. Is it cyclic?
Yep.
Is it completely conjugated?
sp2 hybridized.
What's the hybridization state of carbocations?
sp2.
Always, always,
So-
without a doubt.
So it would be
It's
conjugated.
conjugated. What is the total number of, and is it planar? Yes, because it's 3 carbons, it has to be planar. What's the total number of pi electrons that are participating in this delocalization? Only 2.
Mm-hmm.
There are no electrons there, these 2, so those 2 electrons are basically spread over all 3 carbon atoms, 2 pi electrons. Do you agree?
Mm-hmm.
Which formula does it fit, 4n plus 2 or 4n? Don't be in such a rush.
You have 0, so it'd be,
N can be any number 0 onwards. Sorry, what did you say?
4n plus 2.
Exactly.
4n plus 2
For N being what?
0.
That's aromatic. So the question is for you to tell me which process cyclopropene would want to do. Would cyclopropene want to get rid of a hydride ion or get rid of a proton?
Get rid of a hydride.
Because that creates something that is really stable because it's aromatic. This creates something that is non. There's no benefit there. Do you guys see that?
Mm-hmm.
Everybody? Yes?
Yes.
Yep.
It's all about aromaticity. Aromaticity is very, very stable. Please remember, anything that's aromatic is extra stable. Okay, please tell me what is the pKa? Oh, sorry, what?
nothing.
Oh, Can someone tell me what's the pKa of any hydrogen on an sp3 hybridized carbon? What's the pKa of an alkane hydrogen, generally speaking? Approximately.
36.
Actually, even higher, 50.
50.
Highest pKa's are for those. Extremely low acidities. They're very, 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 very weak acids. Weakest possible. Okay? Alkanes. However, this guy actually has a decent pKa. This guy, you can use a base to deprotonate pretty easily compared to the others, I mean. Why? Anybody? Anyone?
These.
Because if you get rid of a hydride, you make it.
Hydride,
No,
is
no,
it going to
no,
get
no,
rid
no.
of a hydride?
Never mind. No, we don't want to do that.
It'll get rid of
What
a
is
proton.
it getting? What is the base taking?
A proton.
If it loses a proton, what does it become? What's the conjugate base of this guy? Louder? Exactly. Guys, we've done this. We've done this plenty of times. Here's your acid. What's the conjugate base? Well, the acid is going to lose a proton and leave behind a negative charge. Isn't that right?
Mm-hmm.
Agreed? What can you say about that ion? Is it aromatic, anti-aromatic, non-aromatic? Louder?
Aromatic.
Exactly. Why is it aromatic?
It's cyclic.
Okay.
Conjugated.
Okay.
Planar.
Why is it conjugated?
Because the electrons.
So then what are you assuming? As soon as you say conjugated, what hybridization state are you assuming for that carbon atom? Has to be. Because then, if this is sp2, these electrons will be in the unhybridized p orbital. Isn't that right? Then it's conjugated, it can do resonance. Now it's completely conjugated, it's planar, and then what's the total number of pi electrons?
6.
Which formula does that fit?
4n plus 2.
Just like benzene.
N equals 1.
Just like benzene. Is that aromatic?
Yep.
Very stable. Very stable. So that is why, even though this is sp3 hybridized, and those hydrogens are decently acidic because they create a very stable aromatic conjugate base. Do you guys see that, everyone? Yes?
Mm-hmm.
Sure.
Yes.
What is which part? You got to voice the no. When you say no, which part?
How is this different from the cyclopropane?
Which cyclopropane?
The anti-
Losing a proton or gaining or losing a hydride?
losing the proton.
So losing a proton, it became this. Isn't that right?
But that's also because
Yes, I agree. But what's the total number of pi electrons in this case? There are 2 pi electrons here and 2 electrons right there, isn't it? What's the total number? Which formula does it fit? Does it fit 4n plus 2 or 4n? Is there any value of n that will make 4n plus 2 be equal to 4? That's the point. So it fits 4n, which makes it anti-aromatic.
but that has 6.
That has 6, which makes it what?
Aromatic.
Which makes this aromatic. And what about aromatic? What is so great about aromatic?
Stable.
Most stable.
It's very, 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 very stable. It's extra stable.
So if a process is creating something that's extremely stable, is that process a good process or a bad process?
Good process.
Does that make sense? That's basically it. That's basically it. So if the outcome of the process is aromatic, would that process happen?
Yes.
Agreed? But if the outcome of a process is anti-aromatic, would that want to happen?
Maybe. No.
If there's a choice between the two, right? But if there is no choice between the two, well, anti has very low stability, even lower than baseline. Why would something that is okay want to become less stable? There's thermodynamically nothing to be gained there. Does that make sense, everybody? Yes? Okay. Sure? Then my next question for you is, if you understand this, could you draw out cycloheptatriene? Cycloheptatriene. And tell me if cycloheptatriene would want to donate a proton or donate a hydride. What process would cycloheptatriene prefer to do? Did that make sense, Carrie?
Yes.
So it's all about when a process is happening, whatever is created, is that stable or not? That's the criteria.
So it wants stability.
Exactly. So the question I'm asking is, cycloheptatriene, by the way, is cycloheptatriene aromatic, non or anti? No. Everybody agrees? Okay, so will it donate a proton or will it donate a hydride?
Hydride.
Why?
Because it'll make a carbocation and then it'll have 6.
Exactly. It all comes down to that. If a proton were donated, one of these hydrogens was taken as a proton, what would be left on that carbon?
And as
So negative charge, right?
yeah.
Pair of electrons, hence a negative charge. Is that aromatic, anti, or non?
Anti for
Anti, or it could also, if this were sp3, then it would be
No.
non. Which is better, anti or non?
No.
no.
Make sense?
Yep.
But if this were to lose a hydride, what would it become?
Aromatic.
Now there's a carbocation there. That carbon definitely is sp2. There's no two ways about it. So is this aromatic, anti-aromatic, or non-aromatic?
Aromatic.
Do you all agree with Dash? This is aromatic. So which of the two pathways will happen?
The hydride. Donating a hydride.
Does that make sense, everybody? Yes.
So because it has a carbocation, can
Yes.
we still do resonance?
Yes, absolutely. Resonance is not about if I have a chamber full of water and right next to it I put an empty chamber and then I take away the boundaries because so they merge, can the water from here flow into the empty space?
I see.
That's the idea. Resonance is not just, it's about providing these parallel chambers that merge into each other, and how much ever electron density there is flows right through them. So whether that was a carbocation or not, as long as it has an unhybridized p orbital. That's the idea. Does that make sense, everybody with me so far? Yes? Questions? So those are aromatic ions. Ions can also be aromatic, same criteria, no difference, as long as those criteria are met. Okay. Does anybody remember the meaning of the word heteroatom?
Carbon attached to another atom other than hydrogen.
What is a heteroatom, anyone?
Not carbon or hydrogen.
Not carbon, not hydrogen. Exactly.
Not carbon or
A
hydrogen.
heterocarbon is any atom that's not carbon, that's not hydrogen. So another category of aromatic systems are rings that have a heteroatom in them. Heterocyclic rings. Rings that have a heteroatom as part of the ring. For example, pyridine. Pyridine is this. It's a heterocyclic ring when nitrogen is one of the atoms in the ring. Guys with me?
Yep.
Is it aromatic, anti-aromatic, non-aromatic? Because nitrogen has a lone pair. So,
Anti.
is it cyclic?
It's cyclic.
Is it completely conjugated?
Yeah.
Is it planar? Just like benzene, right? Six atoms should be planar because benzene is planar. Agreed?
Yep.
How many total pi electrons? How many electrons participating in resonance?
8.
Is it 8? Let's process. You got to pause. What's the hybridization state of this nitrogen atom?
sp2.
If it's, did I hear sp3? Hope not. Why? Because there's a pi bond. Do you
One
guys
pi-
remember this from last quarter?
One pi bond
Any
is
atom that's making one pi bond has to be sp2. Any atom that's making two pi bonds has to be.
sp.
So it's making a pi bond. So what is the hybridization state of that nitrogen atom?
sp2
So where do they live?
in the unhybridized p.
Do they? Pause. Process through. What kind of bonds do hybrid orbitals make? Guys, this is from last quarter. What kind of bonds do hybrid orbitals make? Sigma bonds. Perfect.
Sigma bonds.
What kind of bonds do unhybridized p orbitals make?
Pi bonds.
Always. Always. There's no exception to that. So, if it is sp2 hybridized, agreed?
Mm-hmm.
How many hybrid orbitals does it have?
3.
Louder, please. You're right. Just say it louder. Don't be so timid.
That's free.
Agreed? Everybody okay?
Yep.
How many unhybridized p orbitals does it have? Everybody okay? So, let's think about this. Sigma bond, what is being used for nitrogen? Our focus is nitrogen right now. Which orbital is being used for the sigma bond? Hybrid or unhybridized?
Hybrid.
Gone. Agreed?
Mm-hmm.
Another sigma bond, what is being used for that? Hybrid, unhybrid?
Hybrid.
Gone. One pi bond, what is being used for that? Hybrid or unhybrid?
Unhybrid.
What's left?
A hybridized
That's where your
orbital.
lone pair is. So you
So
have
the
to
one-
work through it. That's the only place available for the lone pair to live in is whatever is left for it. You guys see that?
Yep.
So can electrons in a hybrid orbitals be part of resonance?
Yes.
No.
No.
Never. I know you wanted to say no. Just like automatically just bubbles out. Only unhybridized p orbitals participate in resonance. Only. So if there are electrons in the hybridized orbitals, can they be part of resonance? No, not at all. So now if you're counting the total number of pi electrons that are actually delocalized, how many would there be?
There would be 6 pi electrons.
Like benzene.
Exactly. This one is not part of resonance. Those 6 are. So is it aromatic, anti, non?
Aromatic.
Do you all agree? Does that make sense? Yes, so far?
Yep.
Yes, Vincent.
So can you go over the whole hybridized and unhybridized thing again? So
Are you
one
going
of
to take me back to week 3 of last quarter?
them-
Kinda.
kind of.
What specifically are you asking?
So you said one of the sigma bonds were
Sigma
hybridized?
bonds only use hybridized orbitals. They never use unhybridized p orbitals.
And then the
Never.
pi
Pi
bonds-
only use unhybridized p orbitals.
Mhm.
Can't switch. The role of the hybrid orbital is to bring atoms together so a sigma bond can be created. Now they are stuck together. And notice then what happens to the p orbitals that are parallel. Now they can make a pi bond with each other. Make sense? So that's something you got to remember.
Yeah, so that's why we have like on the left, one we counted as sigma of the left of the end, the right we counted as sigma, and then the
That's
pi.
not the point.
No?
That's, again, we've done all of this last quarter.
Uh-huh. That's my hardest subject.
Well, can't forget, can't. What is the rule about sigma? Between two atoms, whatever they are, x, y.
One sigma bond.
Only one sigma
Only
bond
one
is
sigma.
possible.
Only one
Only
sigma
one
bond can be
sigma
formed.
bond between two atoms possible, but there must be one. There has to be one sigma and only one sigma. Isn't that right? Do you remember that?
Yep.
One sigma and only one sigma. And if there are other bonds between those two atoms, they will have to be what?
Pi.
Pi, well, yeah.
Whatever they are. So if these two atoms have two bonds between them, I'm talking about the carbon and nitrogen right here, one of them has to be
Oh, no.
One of them has to be a pi bond.
sigma. Let's always start with sigma because unless there can be sigma, there can be no pi.
Okay.
Sigma happens first, pi is after. So think about sigma first. So if there are two bonds between these two atoms, first has to be sigma. Whichever one, who cares?
First
One
bond
of
is
them
formed
has
with
to be
sigma.
sigma. So what would the other one become?
A pi.
Pi.
But then now if you're looking at these two atoms,
Sigma.
there's no pi.
There's a sigma
No,
and there's
that's
no
what I
pi.
was saying, but I guess I said it wrong.
No, but I didn't understand the question then.
Yeah.
Are
No.
you just confirming that?
I was just confirming that that was sigma, sigma, and pi.
So it's not about right or left.
Mhm.
It's about how many bonds are between the atoms.
Oh, no, yeah, no.
That's what matters. If I were to draw it differently and write it this way, would that change?
Yeah, I mean, no.
Right? It'll just be sigma, pi, sigma, but everything else is
Yeah.
Makes sense, everybody?
Yep.
If that makes sense, please tell me, is this aromatic, anti-aromatic, non-aromatic? And don't jump to a conclusion, process through it. Please remember, if something can be aromatic, they want to be aromatic because this is stable. So if there were any way this could be aromatic, they would want to be aromatic. So is this aromatic, anti-aromatic, non-aromatic? So is it cyclic?
Yep. It's
Is
cyclic.
it planar?
Yes.
Yep.
Is it completely conjugated? That's where you got to pause. This is where you've got to process. What do I mean? So we have two options here, guys. One option is, what's the hybridization state of that nitrogen atom?
sp3.
Okay? If it is
4
sp3, can this atom be part of resonance?
No.
Everybody okay?
Mm-hmm.
If this is sp3, what would be the classification of that molecule? Aromatic?
Anti-aromatic.
No, Claudia, slow down.
Okay.
If this is sp3, is it conjugated?
Oh no.
No, right?
So it's
sp3
not
can't do
aromatic.
resonance. So if it cannot be conjugated, what is it?
Non.
Everybody agrees?
Mm-hmm. None.
That's first option. We're not done though. We all agree with this though.
Mm-hmm.
Let's look at another option. What if this is not sp3? What if it is sp2? If it is sp2, which orbital would those sit in?
A p orbital.
If they are in p orbital, can they be part of resonance?
Yep.
If they can be part of resonance, is this completely conjugated?
Yes.
If this is completely conjugated, is it aromatic, anti-aromatic?
Aromatic.
Aromatic.
Because the total number of pi electrons is
6.
6.
we all agree?
Yes.
So here's the question. Which is better? Is it better for something to be aromatic or is it better for something to be non-aromatic?
Aromatic.
If there's a choice.
Aromatic.
So what would you go with?
Aromatic.
sp2 aromatic. Absolutely. So you kind of have to evaluate. Which means Vesper isn't always correct. Vesper isn't always right because Vesper doesn't factor in this stability that comes from something being aromatic. Vesper doesn't This thing wasn't there when Vesper was figured out. Does that make sense, everybody? Yes? Good? So then tell me, same thing, same question. Aromatic, anti-aromatic, non-aromatic. If you're following the process, so you got to process through. Oops, what are you doing, Samantha? Oh, what are you doing, Samantha? Let me fix it. It's not done. There we go. Furan. It's drawn badly, but 5 atoms. It's called furan. Is it aromatic, anti-aromatic, non-aromatic? Lots of fun stuff.
Cyclic.
Well, now it's got 4 electrons.
So you're saying oxygen has 4 lone pair,
Yeah.
non-bonded
There's 4 electron
electrons, right?
groups
Okay, good.
total.
Yeah, and maybe that's why you're thinking.
Yeah.
Pause. You gotta slow down. Slow down. Is it cyclic?
Yep.
Is it planar?
Yes.
5, yes, it will be planar. The question is it completely conjugated? So, what's the hybridization state of this oxygen atom?
4 electron groups.
sp3 according to Vesper.
Mhm.
Vesper says sp3. Agreed?
Yep.
If it is sp3, is it completely conjugated?
No.
So what is it? Anti, non-aromatic, which what?
Non.
Agreed?
Yep.
But what if this were sp2 hybridized? Because again, Vesper is a model. This is a theory which you have to adapt based on observations. This is where Vesper doesn't work. So if it were sp2 hybridized, yeah, I'm listening everything. And I love it when I see the dots connecting. If it is sp2 hybridized, by the way, just for bookkeeping purposes, how many hybrid orbitals would it have if the
It would have
oxygen were sp2?
sp2.
How many hybrid orbitals will it have?
3.
And how many unhybridized orbitals will it have?
1.
Okay. Is that a sigma or a pi bond? If it's sigma, which orbital is used?
Hybrid.
Is that a sigma or pi?
Sigma.
Which orbital is used
Pi.
for that? Agreed?
Yep.
Everybody okay?
Mhm.
So which orbitals do the lone pairs sit in?
1 unhybridized, 1 in another.
One has to go
But which
to
one participates in resonance? Both or just one of them?
the unhybridized.
Now you can tell me, if it were sp2 hybridized, would this system be aromatic, anti-aromatic, non-aromatic? What is the total number of pi electrons that are actually participating in resonance? Because what's the total number of electrons?
6.
6. Only one of those electrons actually is part of the resonance because it's here. The other lone pair does not because it's in a hybrid orbit. You guys seeing that, everybody?
Yep.
So what would it become then?
Aromatic.
What's the better option, non or aromatic?
Aromatic.
Furan is definitely aromatic. Definitely. So the point I'm trying to make here is, guys, models that you've learned in Gen Chem and beyond, those are models. And models we should always be able to adjust our models if it doesn't fit the data. Data is real. Observation is real. And then the model needs to be tweaked to fit that data. Does that make sense? Everybody okay? Is everybody following that? Okay. Cool. Let's look at this worksheet, guys. I gave you all a worksheet with a lot of structures drawn. And the question is, label them as being aromatic, anti-aromatic, or non-aromatic. You guys with me?
Yep.
Okay, the first one. Are we going to think about that?
That's the only one I got now.
So then say it loudly.
Aromatic.
That's benzene, right? Everybody sees it?
Yep.
Okay,
Benzene.
second one. What about the second one?
Anti-aromatic?
Slow down. Try to not be so fast with your conclusion. It is, yes, there is a negative charge, but there are also 3 double bonds. Isn't that right?
Mm-hmm.
Oh, yeah.
Isn't that right?
Yep.
So what's the hybridization state of that carbon atom?
sp2.
Because there's a pi bond. If there's a pi bond, it has to be sp2. There's no option. Are you guys with me?
Mm-hmm.
Everybody?
Yep.
If that is the case, which orbital are these lone pairs in?
And unhybridized.
Are they? Again, that's what we have to process through. Once again, how many hybrid orbitals?
They're free.
How many unhybridized orbitals?
1.
Which orbital is used for the sigma bond?
1 hybridized orbital.
Which orbital is used for this sigma bond?
1 hybrid orbital.
And which orbital for the pi bond?
1 unhybridized.
What's left?
1 hybrid.
Those electrons are not in the unhybridized, they are actually in the hybrid orbital. If they're in the hybrid orbital, can they be part of conjugation?
No.
No.
So should we count them?
No.
No. So what is the actual total number of pi electrons?
6.
Only. So what would that make it? Aromatic, anti-aromatic, non-aromatic?
Aromatic.
Absolutely. Does everybody see that? With lone pairs, you got to process. Where are these lone pairs located? Then decide if the lone pairs should be counted as part of the conjugation or not counted. Make sense, everybody? Please remember, only electrons in hybrid orbitals can do resonance. Sorry, I think I said it wrong. Only electrons in the unhybridized p orbitals can be part of resonance. If electrons sit in hybrid orbitals, they cannot be part of resonance because they're orthogonal. They're not parallel, they're actually at a 90-degree angle. Can't do resonance. Everybody okay? Make sense? So let's look at the third one. What do you think?
Anti-aromatic.
Are you sure? Pause. Are you sure? What is the third one?
Oh.
Yeah.
It's non.
Do you all agree? There is an sp3 hybridized carbon which no way, because it has 4 sigma bonds, this guy. Can we ever imagine an atom with 4 sigma bonds to not be sp3 hybridized? Is that possible? Not at all. If there are 4 sigma bonds, it needs 4 hybrid orbitals, which means it has to be sp3 hybridized. If it's sp3 hybridized, it can't be part of resonance. So what is that one? What did you say that is?
Non.
Non. Okay, what about the next? Cyclopentadiene.
Non.
We've already done that. How about cyclopentadiene cation?
Anti.
Was that anti?
Yes.
Everybody okay? Right? Because there are no electrons there, but these are 4, so 4n, not 4n plus 2. Everybody okay?
Mm-hmm.
This is anti. What about the cyclopentadiene anion?
Aromatic.
Now it fits 4n plus 2 because this has 4 pi electrons, but this has 6 pi electrons. So that's aromatic. This is active. Everybody okay?
Yep.
How about the next one? Oh, did we already do this? Yeah, this is pyrrole. I just drew it differently, but pyrrole. Everybody agrees that's aromatic?
Mm-hmm.
How about the pyrroline, I can write it, I can't say it. The cation, if pyrrole acts as a base and takes a proton, what is that? Did you say non? Why did you say non?
Is it sp3?
Why is it sp3? What is the it, first of all? What is sp3?
Nitrogen.
Nitrogen. Why is nitrogen sp3?
4 sigma
4
bonds.
sigma bonds. If there are 4 sigma bonds, we don't have a choice. It has to be sp3, then therefore it's non. Is everybody on the same page here?
Yes.
Yeah.
Okay, next one, cyclobutadiene. We've done that one. What do you think?
No.
No?
No.
Oh, no, why not? Cyclobutadiene.
It's anti.
It
It's
has to be
anti.
anti because the ring is so small that even though it's putting a lot of stress,
It's anti.
it cannot twist out of planarity. It doesn't have that switch. So it will be anti. What about that weird bi-anion? I don't even know what to call it. But how would you categorize this plus here, minus here? Would that be aromatic, anti-aromatic, non-aromatic? A 4-carbon ring has to be planar. 4-carbon ring doesn't have enough flexibility to not be planar.
It can
Has
be
to be
planar.
planar. So will this be anti, non, or aromatic?
I think it's not.
Why is it non?
No.
No, I'm asking. I'm asking.
Because if I'm understanding, the lone pairs we can assume it's sp3.
Why?
Because don't you have to plot the hybrid orbitals first before you put?
No, there's no such rule. There's no such rule that you have to fill hybrid before you fill this. It depends on what makes more sense. So, is it aromatic, anti-aromatic, or non-aromatic? Why is it non? Okay, so yes, is it cyclic?
Yes, it's
On the
cyclic.
list. Is it cyclic? Yes. Is it conjugated? Well, that depends. So let's think about it. Can that do resonance?
Yes.
Because it has an unhybridized p orbital. Isn't that right?
It has an
Carbocations are
unha-
always sp2 hybridized, which means there's an empty p orbital. Agreed?
Yep.
Can this do resonance?
No.
This is where we pause. Okay, let's see. Which is better? Okay. If it were sp3 hybridized like Vespa says, can this do resonance?
No.
Vespa says this should be sp3, right?
Yep.
If this were sp3, can that carbon be part of delocalization? No. In that case, it would have to be no. But what if we assumed that it is actually sp2? This carbon is sp2. Then where do the lone pairs sit?
They'll be in an
In what?
unhybridized orbital.
Because you got sigma, 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 3 hybrid orbitals gone. The only thing left is the unhybridized p orbital. Does that make sense?
Yep.
Everybody okay?
Uh-huh.
Okay. So if that's the case, what's the total number of electrons in resonance? 4. If the total number of electrons in resonance is 4, what does it make it?
For
Aromatic, anti-aromatic, non-aromatic.
anti.
Non is better. The only problem is, oh, actually, wait a second. No, you can. I was thinking about the shape of the ring, the size of the ring, and is the ring big enough to accommodate a tetrahedral carbon with 3 trigonal planar carbons? We might have to look at the rigidity of the ring itself to see if that's possible. But do we understand the process? What we are doing here? We have to make a model and see, okay, is this ring possible or not possible? Okay, what do you think about the next one? The dianion.
We do that one.
You saying aromatic? Why are you saying aromatic?
Assuming the lone pairs are in an unhybridized orbital.
Exactly. In that case, we are assuming both of those are sp2 hybridized, which means there are 6 pi electrons would be aromatic. Make sense, everyone? Yes?
Can you quickly explain why we are assuming sp3?
Because that gives us stability. Nature is going towards stability. So by assuming it's sp2, we can then say those lone pairs are in unhybridized p orbital, which makes the whole thing be aromatic. And aromatic is always way more stable. So we should go towards higher stability. Which part is causing
Yeah.
discomfort?
So, if we see it a negatively charged,
You got to process.
We can assume either.
You cannot. You got to go through the, if this what, which is better?
With a negative, we can assume that there's SP2.
Again, depending on the system. There actually it was making things worse. If it makes things better, then yes. What do I mean by better? Stability.
Like if it was a different structure that had 2 pi bonds already in it and then an anion.
Same
that
thing.
would
We
give it
did that.
aromatic.
Yeah, right there. We did that. Because whichever allows us stability. So let's go through this one more time because then we've got to go through others. But let's do this one more time, guys. For an anion, there are 2 options, right? It can either be sp3, agreed? Those carbons right
using
there,
Vesper.
agreed?
Yep.
If those carbons are sp3, can they do resonance?
No.
If they cannot participate in resonance, what is the classification of this system? Aromatic, anti, non.
Non.
Do you all agree? Everybody okay?
Those are negative, right?
Yes, I mean, because there's a hydrogen there. Yeah. Okay, so that's one side. Everybody okay?
Yeah.
Now, let's look at the other side. What if these atoms were not, there's also hydrogen there, guys. Please, I'm not drawing the hydrogen, but there's a hydrogen there. What if this were sp2? What if? Where does it take us? Go ahead, Carter. What are you saying, Carter?
You would put the lone pairs in an unhybridized orbital.
Do you all agree with that? Everybody? Sigma bond, hybrid gone. Hybrid 1 gone. Sigma 2, hybrid 2 gone. Sigma 3, hybrid 3 gone. What's left?
An unhybridized orbital.
That's where the electrons are. You guys with me?
Yep.
Everybody? So, these are in the p orbital. In this example, let's do the same with those. If that carbon were also sp2 hybridized, where would the electrons be? Where would the lone pairs be? Do you all agree with that? Because
Yes.
again, there are 3 sigma bonds, 3 hybrids gone. The only thing left is the unhybridized, so this will be in the unhybridized as well. Agreed?
Yep.
So then, what's the total number of electrons delocalized?
6.
We've been with me? That can do resonance, this can do resonance, this can do resonance. 6 total electrons. Which formula does it fit? 4n plus 2 or 4n?
4n plus 2.
So what does that make this?
Aromatic.
So what is better? Is aromatic better, more stable, or non-aromatic more stable? Which of
Aromatic.
these two is better option?
Aromatic.
So we are going towards that. Make sense, everybody?
Yes.
Does that sound okay?
Yes.
Carrie, so with the negative charge, you got to pause. When there are lone pair of electrons, you got to pause and make sure where are these lone pairs sitting? Where do they live? Because that will decide whether you should count them towards the pi electrons or not count them towards the pi electrons.
so if there was 2 hydrogens on that and it was sp3 and then negatively charged, then it could not because all of them.
Say that one more time.
If there was.
I think I've heard, but I think that's not possible.
Yeah, that's.
If there's a carbon with 2 hydrogens and a negative charge, then there's only 1 bond to be made, right? How can it be cyclic? The first criteria is it has to be cyclic. Does that make sense? Anything else, guys? Okay, let's look. Let's look at the next one, guys. What do you think? That's naphthalene.
Aromatic.
Because it's benzenes fused together. Isn't that right?
Yep.
How about the next one? I think we've done quite a few
Yeah.
of them. So can I skip and go to this guy? Because that looks interesting.
Okay.
Another cat anion. Cat anion.
That looks interesting. What do you think?
Well,
Look at each ring one at a time. Don't look at the whole thing. Look at one ring one at a time. Each ring one at a time. And then decide. So what do you think? If I hide this thing for now, is that aromatic, anti-aromatic, non-aromatic? If I hide this,
none.
have you done the math? Is it that rest of it, is it anti?
It would be aromatic.
It is aromatic. Do you all agree? Yes? Okay. How about this part?
It's aromatic too.
Do you all agree? So then the combination,
So if you have one that's aromatic, one that's not, is it not aromatic?
hopefully we won't see that because then I think the whole thing becomes very, I would call the whole thing non-aromatic.
Okay.
Absolutely. Because, does that make sense, everyone? Okay. How about the next one? Very quickly, guys. What do you think? Do you all agree? Okay. How about the next one? By the way, the next one is one of the bases used in DNA, RNA. I forget there's a name for those bases. Right, there's this whole group of bases, guanidine, and there's quite a few of them.
Bimine.
There's a name given to them collectively, which I can't remember what the collective name is.
It's a pyrimidine.
What about this? This is one of them. This is not pyrimidine. This maybe guanidine, but I'm not 100% sure. But not pyrimidine. That one does not have oxygen. What would we classify this as? Don't jump to your conclusions. Pause. Pause. Think about this. Is it cyclic?
Yes.
Is it planar?
Yep.
I think so.
Is it completely conjugated? The
Yes.
answer is yes.
Yep.
Let's process how. What's the hybridization state?
SP2.
How about this?
SP2.
How about this?
SP2.
How about this?
SP2.
How about this?
SP2.
Right?
Yep.
Those are all sp2's, period. There's no doubt about them. What about the nitrogen? It has lone pairs. What about the nitrogen? If it's sp3, that becomes non, right? What if it's sp2? Where will those electrons be?
In the unhybridized
Do
orbital.
you agree? Because there are 3 sigma bonds. If they are in the unhybridized p orbitals, are they part of resonance?
Yes.
So then what is the total number of resonance electrons in the ring?
6.
Not count, that's not in the ring.
So it'd be 6.
6. So what is it?
6.
So what is it? Aromatic, anti-non? Absolutely, it is aromatic. Does that make sense, everyone?
Mm-hmm.
What about the yes, sorry.
How does that not factor into the resonance?
So it does delocalize, but does not contribute to aromaticity. Resonance is not equal to aromaticity. Aromaticity goes even a step beyond resonance. Not everything that has resonance is aromatic, right? But everything that's aromatic has resonance. Does that make sense?
I'm trying to figure
So,
out, how does the math then with the
so that's why those electrons are not counted for the aromaticity.
I'm confused about the math then for that.
Why?
What is the role of the electrons?
Because they're in the ring.
Okay.
Only the electrons that are in the ring that are part of resonance should be counted.
Okay.
The ones that are outside shouldn't be counted. So it's because these were on the ring, we counted them. If they were outside, we won't count them.
Okay.
Next one, what do you guys think, guys? What is it? Aromatic, and we haven't, I want to get to the last two very quickly.
Aromatic.
Really? Sure?
Wouldn't it be
Or?
None.
So which is better?
non?
I would go with that. But if, let's say the question is, assume planar, which means they're not giving you the option of non-planar, then it is anti-aromatic. Does that make sense? Sometimes questions will say, assume planar, which means we don't have the flexibility of non-planar. Then you have to go with planar, and whatever that leads to. Does that make sense, guys, what I'm trying to say here? Sure? I'm seeing some confused faces. So sometimes the questions will say that. Okay, what do you think about the next one?
Wouldn't that be aromatic?
Slow down.
No. No.
What is it?
It's non.
Why is it non?
Because there's an SP3.
There's an sp3
There's an
carbon which cannot be anything but sp3. Do you all see that?
Okay.
Okay, I really want to talk about the last two. What do you guys think?
Aromatic's the first one.
Why?
Because there's 6 electrons in
Exactly. Which 6? We're counting 2 of those because the other 2 will be in the hybrid. These will be in the sp2 orbital, but those will be in the unhybridized p orbital. Agreed? So only the unhybridized electrons do resonance. So 2, 3, 4, 5, 6. What about that carbon? Can it do resonance? Can it participate in conjugation?
No.
Isn't it sp2 hybridized? If it's sp2 hybridized, it can participate in resonance.
I thought you were talking about the double bond.
Oh, the atom.
Okay.
Absolutely. We're not counting those electrons for aromaticity in the ring, but can this do resonance? Absolutely. So what's the total number of pi electrons? Notice how the 6th number keeps coming back. Absolutely. What about the next one? That's very, very interesting as well.
It could be anti or non.
Choose one. Oh, I see why you. Oh, no, be careful. What is on boron?
How many electrons does this have?
Is it aromatic, non-aromatic, anti-aromatic?
Wait, is it non?
Why are you looking at me? What is it?
Non?
Boron. What's so special about boron?
It can make 3 bonds.
It can only make 3 bonds. Why? Because it only has 3 valence electrons, right?
Yep.
So a neutral boron, does it have any electrons on it? Lone pairs on it?
No.
Can it ever have octet? So, if it is trigonal planar, 3 sigma bonds, trigonal planar, what should be the hybridization?
sp2.
Which means it has a p orbital, but that p orbital is? Can it do resonance though?
Yes.
Absolutely, electron density can pass through that orbital. Agreed?
Yep.
Can this do resonance?
Yes.
How about that?
Yes.
How about that?
Yes.
How about that?
Yes.
How about oxygen? Because it has 2 lone pairs, but only one of them in the p orbital if the oxygen is sp2 hybridized. Agreed? As we saw for others. So what's the total number of pi electrons?
6. So it's aromatic.
It's aromatic. Yes.
Okay, can we go back to another that's
Which
been
one?
bugging me since I started with
Which
this
one?
page? The oxygen in what, I can't name it, but the
That's
oxygen in what looks like a benzene ring.
Ooh, I see why
Because
that's
I
bothering
count
you.
30 so here's my confusion.
Yes.
I count 31 electrons.
31?
Yeah, because it's gotta be odd.
Are you counting all electrons?
Yeah, and-
No, only electrons that are part of
Well, I know,
resonance.
but
Oh,
there's that
oh,
one
I see,
going.
I see, I see. So maybe others will tell me what's wrong with my structure. Because this is something that I kind of harp on all the time. What's wrong with that structure? I see what you're saying.
Oxygen is making 3 bonds.
So what should it also have?
Positive charge.
Oh.
That's what I'm
Positive.
missing. That's my mistake on the structure.
It's an
It should
oxygen.
have a positive charge.
Okay,
'cause
that's, okay, now
then
I got it.
Perfect.
All right. thank you.
Absolutely.
It's an oxycap.
Exactly. It has to be positive otherwise. Can you guys please fix that structure?
Yep.
Gotcha.
Okay. Everybody okay so far? Do we understand those rules? I can see you guys are having a great time, having so much fun today. Right, fun? Yeah. Can we go to the back page, guys?
Sure.
What was that?
Brain cells spinning.
Oh, okay. I hear you.
Gotcha.
Till you come home from the gym with your whole body screaming of pain, you haven't built any muscles.
True.
So that's okay. Make them work. They'll get stronger. Right? It's okay.
Yep.
Let's look at the next question, guys. So the question is, select which of the following will be better at the property mentioned. So when you're looking at furan and pyrrole, which of those will be a better base? Furan or pyrrole? What does a base do?
It accepts electrons.
No, not really. Not at all. What does a base do?
It donates.
Donates a what?
Donates protons.
Really?
Wait, it accepts protons.
Thank you. So the question is, which of these two substances will take a proton more easily? Why? Are you sure? Don't jump to conclusions, is my suggestion. Let's figure it out. What does it become when it takes a proton? A base takes a proton, isn't that right?
Mm-hmm.
Please draw the conjugate acid. If this took a proton, what will it become? Draw the conjugate acid. And then decide which is a better conjugate acid. So, do you agree that this is the conjugate acid from furan?
Yep.
And this is the conjugate acid from pyrrole. Agreed?
Yep.
Now, can you tell me, please, was the original substance aromatic, anti-aromatic, non-aromatic? Was this aromatic, non-anti?
It is aromatic.
Do you all agree? Can I just say AR? Everybody okay? How about pyrrole? Was it aromatic, anti-aromatic, non? Aromatic. Same reason as furan. Okay? Now can you just evaluate the conjugate acids and tell me if this is aromatic, anti-aromatic, non-aromatic? Same rules.
Anti.
What is it? Is it cyclic?
Yep, it's cyclic.
I'm looking at the first one. Is it cyclic?
Mm-hmm.
Is it planar? 5, you can assume planar.
Yep.
Is it completely conjugated? The answer is heck yeah.
Yep. SP.
That oxygen is sp2 hybridized. If
With
it's
a plus
sp2
charge.
hybridized, every single atom is able to do resonance. It's conjugated. Agreed?
Mm-hmm.
What's the total number of electrons in resonance?
6.
Even if it's not drawn, you got to be able to figure out that, yup, it originally had 2 lone pairs, 1 lone pair is gone, it now has 1 left over. So if it has 6 pi electrons, is it aromatic, anti-aromatic, non-aromatic?
Aromatic.
So aromatic is still aromatic, agreed?
Yep.
What about this guy? Is this aromatic, anti-non? Why?
That's because it's an SP3.
SP3.
That guy has no choice because there are 4 sigma bonds. If there are 4
SP3
sigma bonds,
hybridized
it has to be
nitrogen.
sp3. So, please notice, aromatic stayed aromatic, but aromatic became non. Which is a better path?
Aromatic to aromatic.
Do you guys agree?
Mm-hmm.
This created something less stable than itself.
Mm-hmm.
But this created something that's about as stable as itself. We didn't lose stability. So which is a better base of the two?
The upper one, what's the name?
It's called furan, but the name's not important. But yeah,
Furan?
absolutely. Do you understand that? Everybody. Okay, look at the next one. You're looking at those two compounds and you need to decide which of those is a better acid. What do acids do?
They donate protons.
So creating a conjugate base, right? Draw out the structures of the conjugate bases and then decide which conjugate base is either more stable than what you started with or as stable as what you started with, and then decide. What do you think?
Base.
Anyone? If the first one lost a proton, what would it become?
It would have a negative charge on that top carbon.
Agreed? Is this aromatic, anti-aromatic, non-aromatic?
Assuming that electron is in that lone pair is in an unhybridized orbital.
What will your conclusion be, Carter? Agreed? Everybody agrees? Aromatic? Right? So originally, what was it originally? This is aromatic. What was it originally? It was non. So did we become more stable, less stable, or stayed the same?
More
Do you
stable.
see that? Okay, the second one. Originally, is it non-aromatic, anti-aromatic, or aromatic?
It's non.
And then when it loses a proton, what does it become?
Still non.
Still non. If it is still non, which comparing, and again, it doesn't matter which one gives a proton for the analysis purpose, it doesn't really matter. It could have been, you could have also drawn this one.
But it still had an sp3 hybridized.
Exactly. It will still have an sp3 hybridized carbon atom, but that both of them are also non-aromatic. So which is a better option, going from non to aromatic or non to non?
Non to aromatic.
Exactly. So that is the correct answer. Is everybody seeing that? Make sense? Can you quickly tell me for the next one? Cyclopropane or cyclopropene? Which one will be more acidic? Cyclopropene. Why?
Acidic.
Acidic. Slow down. Acidic. Acidic means it's giving a proton. If it's giving a proton, what is it creating?
It would create a conjugate base.
Yeah, but what is that conjugate base is the question I'm asking, really, right? So this is cyclopropane being an acid. Am I right?
Yep.
Is this how do you classify this guy?
sp3.
Non? We're talking about these today.
Yeah.
How about this one?
No.
Do you agree?
Yes.
But cyclopropene, acting as an acid, meaning giving away a proton, will become this. Am I right?
Yep.
Is it, what about this classification of this guy?
No.
Do you all agree?
Mm-hmm.
How about that guy? Which is better? Non to non? Non to anti?
Non to non. So it'd be that guy.
Gotta
Cyclopropane.
look at. We want to not lose stability. We either want to gain stability or at least stay where it was. We don't want to become less stable. Okay, how about the next one? That's actually, those two are also biological bases. Again, don't ask me the names, I don't remember. But you'll probably come across them in biochem and stuff. But the question is, which of those two will be a better base? Anybody? Are they both, is the first one aromatic, anti, non? What's drawn there?
Non.
Really?
Oh, the base.
The first compound that's drawn, is it aromatic, non-aromatic, anti-aromatic?
Aromatic.
Do you all agree?
Aromatic. Okay. I was looking at its conjugate base.
Okay, good. That's a good point. So
Or
what would
conjugate
the
acid.
conjugate base be?
Wait, conjugate acid.
Oh, sorry. Yeah,
I was looking at the conjugate acid.
acid, not base. So what would the conjugate acid be? Nitrogen has?
2 hydrogen.
So then if it is and a positive charge, right?
Yep.
So this is aromatic. What is that?
Non.
So do you all agree?
Yep.
Okay, let's do the same for the other one. Is this aromatic, non, or anti? Aromatic. And if it takes a proton, becomes a, we're looking at base. Takes a proton, what is the conjugate acid of that base? Do you agree?
Yep.
What is that? So which is a better base?
Second one.
Absolutely. Do you agree? Everybody? Make sense? Yeah?
Yep.
So can you tell me the last one? What's the major product? By the way, that's also a biological base. Can you tell me what will be the major product if that guy takes a proton? What will we get? The major product. What reaction are we thinking about? Is this aromatic or not? I have another quick way of figuring it out. Focus on the lone pair. Is the lone pair counted towards aromaticity? Then it doesn't want to go away. But if a lone pair is not part of aromaticity, then go, take me, because it doesn't matter. Does that make sense? That's also another way of thinking about it. So where will the proton preferably go is basically the question here, is that when you have two nitrogens and they're both with lone pair of electrons, but which lone pair of electrons are more accessible for the acid to react with? Why the one on the bottom? So, the point is, are these lone pairs part of the aromaticity? No. Do you all agree? These are not counted towards the aromaticity. But are these part of aromaticity? Yes. So then, these are not part of aromaticity, they are not part of the delocalization, the conjugation, blah, blah, blah. But these are counted towards aromaticity. So, if we destroy those lone pairs, will it affect aromaticity? If those lone pairs were not there, will it change aromaticity or not, right?
Yes.
But if we destroy these lone pairs, would it make any difference?
No.
So where would the protons preferably go? Exactly.
Bottom nitrogen.
Because that does not change the aromatic characteristic of the product. The product is still aromatic because those lone pairs anyways were not counted for aromaticity. Does that make sense? That's basically it. This is aromaticity. the highlights of this chapter are naming benzene compounds that we did yesterday. Please memorize the mono-substituted ones that I listed yesterday on the board. Then the whole idea of what does it even mean to be aromatic? And then using these rules to decide is this aromatic or anti or non and so on and so forth. That's kind of it. So we are going to stop here this quarter. Next quarter we'll go to the next chapter, and which is all about benzenes, by the way, the next chapter. So we'll start that next quarter. I've started making the syllabus for next quarter. I'm not done all the way though. But I was looking at that we have 6 chapters to cover next quarter. So could I